Hey everybody. So we are going to talk about the cross product today. This is a weird one. It's going to turn out to be a fairly ugly formula that we have. It's not terrible. It's doable, but it's not as easy to memorize as some of the other ones. We're not going to completely derive it, but I want to give you a little bit of idea of one way you could go about coming up with this formula, and then I'll present the formula. But here's the idea. Let's start with a little geometric interpretation. The cross product, let's start with two vectors, A and B. I'm just going to draw them. So let's say I have vector A, vector B. So it's hard to imagine. This is actually something that only exists in 3 dimensions. Because what we're going to do with this cross product, I'm going to make a new vector out of this cross product. The cross product is going to be a vector, and what I want is a few things about this vector to be true. So the first thing is, if I imagine these two vectors A and B, imagine they're sitting in like a sheet of paper in a plane, right, touching at their initial points. I want the vector that I'm going to call the cross product to be perpendicular to both of them. Right, so its direction should be along that line, right? You can imagine there's like a little right angle there and a little right angle there, right? Notice though, it could also be pointing along this line, right? If I think of, two vectors, if I think of my pens as vectors, there's a vector going into, or like pointing straight up from them that's perpendicular to both, or pointing straight down from the place where they meet. That's perpendicular to both. That's what I'm trying to draw here. And not only is the direction not unique, the length isn't unique, right? That I could draw, right, this vector here or this vector here, right? Any vector along this line would do. And so I can't say there's the cross product with just that condition. So we're going to add some conditions, okay? So far I've said I want it, let's say this. I'll write the symbol. That's our symbol for A cross B. And I'll say is perpendicular to A and B. That's one condition we want. I want it to, I'll just write respect the right-hand rule, right? So what I mean by this is when I do A cross B, so let's imagine my fingers right now are pointing in the direction A and they curl towards B, then the cross product will be in the direction of my thumb. So in this viewpoint, straight up, right? Some people do the right-hand rule this way, with this finger is A, this finger is B, and then your thumb points in the direction of the cross product. The same right-hand rule that helped us define the XYZ axes, okay? So what that would mean in this picture is now I've cut off for A cross B all these vectors down here, because if I do A cross B, starting with A to B, if I align my fingers with A and curl towards B, right, it's hard to do this in the plane here, but that's the direction we get. And then finally, if we want it to, now we have to choose among all the possible vectors in this direction, right? All the different lengths. The magnitude we want is going to be, so this might seem like an odd choice, but it turns out to be useful down the road. Remember what I said about this stuff, the dot product, cross product. We're kind of just learning a bunch of tools right now. And we're not at the place where they get interesting, right? Like memorizing times tables. So the magnitude is going to be the area of the parallelogram defined by A and B. And what I mean by that is if I were to put a copy of B out here and a copy of A right there, there's this parallelogram. And it has an area and I just pick the vector along here whose magnitude is equal to that area, right? The number, right? The area, of course, the units are different, but we just take the number. I guess they turn out to be all right, which is good. That makes sense. So in any event, let's see how we can at least a little bit fit these three things to a vector. So let's do this. Remember what we're trying to do. I have a vector A, which is A1, B1, oh, sorry, let's start that again. A is A1, A2, A3. B will be B1, B2, B3. And I'm trying to come up with a vector C that I'm going to call the cross product of these two vectors. And what I want is these conditions met. Let's start with this first one. C being perpendicular to A and B means, if you remember from the dot product, A dot C has to be 0 and A dot B, sorry, B dot C has to be 0, right? That's just saying it's perpendicular to both of them, okay? So according to these components here, what does that mean? That means A1, C1 plus A2, C2 plus A3, C3 equals 0. And then B1, C1 plus B2, C2 plus B3, C3 equals 0, right? So all I've written out is these two statements that the dot products are 0. Okay. Now, let's note something. In this, the way I'm thinking about this right now, all the components of A and B are things I know, right? Because I'm going to be given two vectors and I want to find this thing that I'm calling the cross product. So those are known. What I'm trying to discover is how to determine C1, C2, and C3 in terms of the A's and the B's, okay? You might also notice we have two equations and three unknowns, right? When you have that kind of situation, there's often, let's say that, more than one solution, and typically that'll be infinite. For instance, think about having two unknowns and one equation, right? When you have more unknowns than equations, like x plus y equals 1, that's a line. It has infinite solutions. So I'm not going to go through the whole derivation. I'll give you a hint at how it might work out. You could, for instance, eliminate the variable C3, right? If I multiplied, for instance, this top equation by B3 and the bottom equation by A3 and then subtracted them, these two would disappear. And we'd have a single equation with two unknowns, right? Very similar to having something like, it would be a similar equation like, something like, you can imagine the equation 3C1 plus 2C2 equals 0. If you wanted to solve this, there are infinite solutions, but the easiest one to take might be letting C1 equal -2, C1 equal C3, C1 equal 2, C2 equal -3, and then this equation is solved, right? That's an obvious solution you can take. So that's kind of the road. A similar sort of thing happens to that. I'm gonna leave that in your hands. And what that does is let you solve for you get choices for C1 and C2, and you take those and you can plug them back in to find C3 into either one of these equations. It's pretty algebra heavy, but it's totally doable. What will that give you? That will definitely give you a vector perpendicular. You can take a look at the direction and decide if it's going the right way to respect the right-hand rule. If it's not, we simply multiply it by -1. And then we can make sure that its size is the right size by scaling it, right? These aren't necessarily easy problems, but they can be worked out algebraically. What it all works out to, let's make now our definition of the cross product. So we will say, given vectors A, as I said before, and B the cross product is defined as, and we write A cross B, okay, right, distinct from the dot product, and it gives us a vector. And the way we figure out that vector is take the component A2 times the component B3 minus A3 times B2. That's our first component. Remember, these are all numbers. This is a number. Then we take A3 B1 minus A1 B3. And then we take A1 B2 minus A2 B1. Okay. That strange configuration satisfies all of the conditions I mentioned here, right? It will be perpendicular to both of these vectors. It will respect the right-hand rule, and it's the magnitude of this vector will be precisely the area of the parallelogram defined by those two vectors. Okay, so let's do an example. Let's start with that. So for instance, the vector A equals 2, 5, -1, and the vector B equal to 3, 0, 2. Let's compute A cross B. So let's go through this a little slowly. I take A2, B3. A2 times B3. A3 times B2. A3 times B2. Then I take A3 times B1. -1 times 3. Minus A1, where am I looking? There we go. A1 times B3, -4. And then finally, A1 times B2, 2 times 0, minus A2 B1. Okay, so it's a little bit of an ugly computation. Not that anything's difficult, but it's very easy to lose track, lose a negative sign, and so forth. But in the end, that's the vector I got. Let's at least prove one of the conditions is true with this vector, right? Let's see that it's perpendicular to both of the vectors it was made from. So let's look at A dot A cross B, right? So I'm dotting this vector with this vector. 2 times 10 is 20. 5 times -7 is -35. -1 times 15 is 15. And that, of course, sums to 0. And we'll do the same thing with B. We'll dot that with this new vector. So 3 times 10 is 30. 0 times -7 is 0. 2 times -15 is -30. And that, again, is 0. And so, in this case, it works out. And I suppose I'm asking you to believe me that it always works out. You can prove it rather easily, that piece of it, using this. If you dot this ugly thing with one of these and then the other one, it will work out to equal 0 each time. I'm going to let you do that algebra on your own. It's very doable if you want to prove it in the general case. Okay. Let's take a quick look at that with some graphing, with a graphing program. So, one second here. There we go. All right. So here are my two vectors. A was 2, 5, 1. That's the blue one here. And B is 3, 0, 2. That's the red one. The cross product this will compute it for us automatically, is this green one. Let's see if I can get it to let me grab it. There it is, which is exactly what we got. All right, and we can see in space a little bit here. It is reasonably convincing to me that it's perpendicular to both, right? I can't quite get the perfect angle to see it. Maybe right there, it looks like we're seeing the right angle perpendicular to both of those vectors, okay? So we get this, and its length, presumably, if we can imagine the parallelogram defined by those two vectors, right? If we drew them in here, that the area of that would be equivalent to the length of that vector there. Okay, so moving on, let's do a couple more things about the cross product. Let me go back to the paper. Okay, so there are a couple other properties we should mention that are kind of implied by some of the things we've done here. So let's go back to, I just lose what I had in my hand. That's all right. Okay, I'll just write it out here. So let's say we've got our cross product. We've got our vectors A and B, and the cross product, we already know it's perpendicular to both. Okay. It also turns out the magnitude, which I said is the volume, the area of the parallelogram. I'll just draw a picture instead of writing it over and over again, which also turns out to be the magnitude of one vector times the magnitude of other times sine of theta, where theta is defined exactly how we did for the dot product, where theta is the angle between A and B, so that we're choosing the one between 0 and pi instead of going around the long way, say, right? And our picture is something like this. If this is A and this is B, then here's the parallelogram. And the height of this parallelogram you can compute with a little bit of geometry. If this is theta in here, is just B sine theta. So if I take the magnitude of the base times this height, magnitude of A times magnitude of B sine theta, I get the area of the parallelogram. Okay, so that's another neat little consequence of this cross product, right? Again, we're taking the magnitude. I want to make that clear, right? The cross product itself is a vector. This is a number. This equation here lets us know that the area, or sorry, that two vectors, A and B, are parallel if and only if A cross B is the 0 vector. Okay, well, why is that? Again, all of the stuff we're saying assumes that A and B are not the 0 vector, right? So I've mentioned in previous videos, I forget to say that sometimes, we're mostly not considering the 0 vector. It shows up once in a while, we have to be able to deal with it, but most of the things we're talking about vectors with some non-zero magnitude. So if neither of these are 0, the only way the cross product is 0 is if sine of theta is 0, which only happens at 0 and pi, okay? Which means the two vectors are either like this, where we have an angle of pi, or they're like, right, I can't really draw the two of them right on top of each other with an angle of 0, okay? And in both those cases, sine is 0, and that's what we mean by parallel. This is not a great way to check if two vectors are parallel, because taking a cross product is not easy. There is a rule we have for parallel vectors that they're scalar multiples of each other. So if you're trying to see if two vectors are parallel, that's usually the way to check. This is more useful in my experience that you go to take a cross product of something and you get the zero vector and it feels like you screwed up because that just doesn't do the things you want to do. The zero vector is not perpendicular to anything. Well, what it means is you started with vectors that were parallel, right? And it kind of makes sense. Think about this vector here, like these two vectors here, right? If they're laying on top of each other, and I want to make a vector perpendicular to both of them, this vector will do, but so will this one, so will this one. We can spin this any way around, right? If my vector is a vector in this paper, right, this vector straight up is perpendicular to it, as is this vector right to the side, as is this vector to this side. I can spin all the way around, and all those vectors are perpendicular to this one in the paper. So how do we choose one? It kind of breaks everything. We can't do all those things when they're parallel. So we end up spitting out the zero vector, which is kind of a nice consequence. It gives us something we can still work with. It doesn't shoot out an error or something like that. It just lets us know we're asking an impossible task. We can't really do the right hand rule on vectors that are parallel that way. And other various problems. Okay, so let's see. Let's do one other thing with our vector, with our cross product before I jump into a few more properties. One of the things we will like to do with these vectors and the cross product, the finding perpendicular vectors turns out to be very important. One reason for that is it will turn out, right? So similar to how we study a lot of lines when we have two-dimensional geometry or two-dimensional coordinate systems, we'll study a lot of planes. They're kind of the simplest, one of the simplest objects in three-dimensional systems. And vectors and perpendicular vectors play a big role in studying planes. So I don't want to go too deep into the geometry. I'm going to do a whole video on planes, and we'll talk about it more there. But one way we can think about defining a plane is through 3 points. So first, let me convince you that that's true, right? If I have 2 points, as long as they're not the same point, there's a line that those 2 points define, right? How many planes contain that line, right? Well, the plane I've drawn is in this piece of paper, right? Now, if you can imagine for a minute spinning the paper around that line, every different orientation it goes into is a different plane, right? So for instance, one kind of coming straight up, imagine I can keep that line in the same place. Imagine maybe something like a spiral bound notebook, right? If the spiral is a line and you open the cover up, right? It's defining a plane in all those different directions as you open it up. Each one of those contains the line. So two points isn't enough for a plane. But as soon as I throw a third point in, now this piece of paper is the only plane that contains these 3 points, right? As long as they don't lie on the same line. They can't be collinear points. But as long as there's not one line that contains them, then they are enough to define a plane. It turns out that's not the easiest way, but it is helpful to understand that that's true. We will often use perpendicular vectors to define a plane because here's what we're about to do. Imagine I have 3 points. I can make vectors, 2 vectors out of them, right? I could make more, but this is all I need. And then take the cross product, and I've got a vector pointing straight up. Once this vector pointing straight up tells me the direction of this plane. Remember the problem before when I had 2 points and I could imagine rotating the plane around it? Once I have this vector pointing straight up, any of those other planes as I rotate aren't perpendicular to this vector anymore, right? This vector is coming straight out of this plane. Any line I draw in this plane will be perpendicular to this vector, okay? And so if we have 3 points, we can make this perpendicular vector, which is what we'll actually use to define planes later on. So we like to find we like to find these with the cross products, right? And at that point, we have a point and a perpendicular vector, and it turns out that's everything we'll need to define a plane. So don't get too bogged down in the geometry of it yet. I just want to go through the process. It's just good practice for vectors. We will dig into planes in later videos until you're sick of them. So let's do this. Let's take 3 points. A is the point 1, 3, 1. B is the point 1, -2, 2. And C is the point -1, 3, 0. Okay. So imagine these are like the 3 points that I have. I can choose any 2 vectors connecting them, right? I could have chosen this one over here and done the same thing. It doesn't matter. So I'm going to choose the vector between from A to B. Oops, I meant to do this. I'm just going to name it U to make things easier. That's going to be the vector. Remember how we find vectors between points. If it's going from A to B, I subtract the components of A from the components of B. So this is going to be 0. Oh, I copied my, I'm going to graph this in a minute. So sorry, I got to change that to a 1 so it works with the graph I have ready. All right, -1 minus 3 is -4. 2 minus 1 is 1. So there's my vector U. And I'll do the vector AC. Same idea. I'm going to call that V. -1 minus 1 gives me -2. 3 minus 3 gives me 0. 0 minus 1 gives me -1. So there's my 2 vectors, like the 2 vectors I've drawn here. Now I'm going to find that vector pointing straight out of the paper by taking the cross product, U cross V. Okay, so let's remind ourselves of this formula. I'll put it here. Okay, so I've got to take the second component of the first vector times the third component of the second vector. So -4 times -1 gives me a 4. Then I subtract the third component of the first vector minus the second component of the third component of the first vector minus the second component of the second vector right here. And so that's 1 times 0 is 1. So that one's done. Then I take the third component of the first vector times the first component of the second vector. So 1 times -2. And then I subtract the first component of the first vector times the third component of the second vector. 0 times -1. So that's another 0. So that one's good. Then first component, first vector times second component, second vector. 0 times 0. Second component, first vector times first component, second vector, and we're subtracting them. So there's 3 negatives. We're subtracting from here -4 times -2. So -4 times -2 is +8, but we're subtracting it, so we get a -8. So there is our cross product. Like before, let's just do a little double check. Let's take, I'm just going to call this vector n just for notation. And let's take u dot n and see what we get. We expect it to be perpendicular. So here's u, 0 times 4. -4 times -2 is +8. 1 times -8 is 0. There we're perpendicular. V times n is dot n, excuse me. -2 times 4 is -8. 0 times -2 is 0. -1 times -8 is +8. And again, we get a 0. So there we are with 2 vectors perpendicular to the ones we started with. Let's get a picture of this in with the geometry I was mentioning. So give me a second to set this up. Let's see, got it. Where did you go? There you go. Okay. So what I've done here, and I had to eyeball this, this is a little applet, it doesn't let me put points in, but I dragged these 3 dots to the points from our problem, and then I made vectors between, right, so this was like our dot A, and I forget which one's B and which one's C, but those are our vectors U and V, and there's the cross product is that long vector pointing out. And now with this, so I'm turning it into an orientation. It's a little hard to manipulate this, but we can see that those two vectors are sitting in a plane, and this cross product vector is sticking straight out of it, right? And that's going to be a tool we use quite often as we move forward, okay? So this is a pretty neat little thing that I just found before making this video. Okay, so we'll hold off on doing any more of that geometry for now. Like I said, we're going to do a bunch with planes in the future. Let's do one last thing. Let's list some properties of the cross product. So these have to be proved. I'm not going to go through them and prove them. Most of them can be proved with some pretty straightforward algebra. So let's say we have vectors A, B, and C, and a scalar C. Okay. So one thing we haven't talked about is the fact that the cross product does not commute. If you reverse the order, oops, let's write this correctly. A cross B is equal to negative B cross A. Right? If I reverse the order, I get the same number or the same vector except in the opposite direction. Okay, so here's one of these things that, unlike most things we've dealt with, does not commute. Okay. And we might have surmised this from one of the conditions we had. We said A cross B should respect the right-hand rule, right? If I'm pointing my fingers at A and they're curling towards B, the vector would point up, right? But if I switch to B cross A, then I got to point my fingers at B curling towards A, and now my thumb is pointing down, right? So it reverses the direction, and we pick up this negative, okay? And again, that you can see if you look at the components and rearrange the way it would if you switch the roles of A and B, you'll see you get the same subtraction problems in the reverse order, which brings out a negative. Okay, then if we multiply the cross product, sorry, if we multiply a vector, if we scale it and cross it with another vector, we can save the scaling until after we do the cross product. Or we can scale the other one and then take the cross product. Okay, so C is a scalar here, not the vector C. There's no bar above it. This is the scalar C. So we're just scaling vectors in each of those cases, but we can do it from any position and get the same thing. What about addition and the cross product? So if I add two vectors and then I cross them with A, what do I get? Well, happily, things distribute. Similarly, in the other direction, if we're crossing on the right, it still works. But it's because we've got something that doesn't commute, it's really important that we check both directions work to see that things don't work out differently, right? It's a very odd kind of multiplication here. Here's a kind of neat one. If we do A dot B cross C, that's the same as A cross B dotted with C. Okay. And then finally, here's another one. A cross B cross C is equal to A dot C times B minus A dot B times C. Okay, so just notice on this side what's happening. A dot C is a number, and then we're scaling the vector B. A dot B is a number, then we're scaling the vector C. So these things are here because, and there's more of them out there. I mean, there's a lot of reasons why they exist and why they might be useful. But one might be that if you have instances where this kind of computation shows up often, this might be an easier way to perform it. I know I would rather do this one than this one. Even if I was working with a computer, this is still easier to program than this is as a way to do you know, this double cross product and so forth. They're also valuable when you're working theoretically, if you're trying to manipulate things when you don't have the actual numbers and you want to see what happens. It might be the case that something like this can cancel with something else in your work. So it's nice just to have kind of like those trig identities where you've just got a whole slew of them and you just use them in various contexts. Let's do one more thing. Just want to talk about this little thing here. This is given a special name. It shows up in some places. They call it the scalar triple product. Okay. A dot B cross C. There's another way we can think of this. If you've seen any linear algebra, if you have a matrix made up of the components, C1, C2, C3, of these three vectors, this thing here is the determinant of those three vectors. Okay. And in magnitude, meaning if you take this determinant, you get a number, but this is now actually like our regular old absolute value because it's B cross C is a vector, but we're dotting with A, so we get a number. We take the absolute value. I still like to call that the magnitude now that we've introduced that term. So we want it to be positive because this can represent a volume of the parallel pipette determined by these vectors. And so I'll draw a little picture of this. Let's say I have vector B right here, C, sorry, I'll call this one A, and C is kind of going back into the page. Similar to how we made a parallelogram, I could make a parallelogram by making copies of B and C, and then I could make another parallelogram by copying B and A, and then I can throw another copy of A over here and a copy of C, and so on and so forth. We get this nice kind of slanty box. This thing gives us the volume of that, okay? Right now, that might seem like a little geometric oddity, but this is a pretty crucial piece of information, right? So let's just suffice to say there are places in science where this kind of a thing is important to be able to do things like volumes, right? You've done integrals, for instance, that have to do with area. There are integrals that have to do with area. And there's some stuff in this construction that ends up mattering for those kinds of things, among many, many, many other things. So like I said, right now, we're learning our arithmetic of vectors. And we will start shortly in the next couple of videos applying them to some more interesting things. Okay, that is it for the cross product. My recommendation is, while there are calculators out there that will do them, and certainly they're not hard to find, and so, right, a professional might use them often, it's not terrible to get a little practice in with them. They end up not being that big of a deal. That formula is ingrained in my brain, and it's actually quicker to pop it out more often than not, especially because sometimes you're working not with actual numbers. You might be doing something theoretically, and so being able to crush through that formula is pretty important. And there's no way to get good at it other than doing a bunch of them. Okay, that's all I'm going to say for now. Thanks for coming. I will see you next time.